Silvanus Thompson. Elementary Lessons in Electricity and Magnetism. This book was written in 1895, so some ideas and units might be outdated, but its heritage value is great. All books on my channel are in public domain. Please, subscribe, like, and comment. Lesson 4. Conduction and Distribution of Electricity. 30. Conduction. Toward the close of Lesson 1 we explained how certain bodies, such as the metals, conduct electricity, while others are non-conductors or insulators. This discovery is due to Stephen Gray, who, in 1729, found that a cork, inserted into the end of a rubbed glass tube, and even a rod of wood stuck into the cork, possessed the power of attracting light bodies. He found, similarly, that metallic wire and packthread conducted electricity, while silk did not. We may repeat these experiments by taking, as in Figure 25, a glass rod, fitted with a cork and a piece of wood. If a bullet or a brass knob be hung to the end of this by a linen thread or a wire, it is found that when the glass tube is rubbed the bullet acquires the property of attracting light bodies. If a dry silk thread is used, however, no electricity will flow down to the bullet. Gray even succeeded in transmitting a charge of electricity through a hempen thread over 700 feet long, suspended on silken loops. A little later Dufay succeeded in sending electricity to no less a distance than 1,256 feet through a moistened thread, thus proving the conducting power of moisture. From that time the classification of bodies into conductors and insulators has been observed. This distinction cannot, however, be entirely maintained, as a large class of substances occupy an intermediate ground as partial conductors. For example, dry wood is a bad conductor and also a bad insulator. It is a good enough conductor to conduct away the high potential electricity obtained by friction, but it is a bad conductor for the relatively low potential electricity of small voltaic batteries. Substances that are very bad conductors are said to offer a great resistance to the flow of electricity through them. There is indeed no substance so good a conductor as to be devoid of resistance. There is no substance of so high a resistance as not to conduct a little. Even silver, which conducts best of all known substances, resists the flow of electricity to a small extent. And, on the other hand, such a non-conducting substance as glass, though its resistance is many million times greater than any metal, does allow a very small quantity of electricity to pass through it. In the following list, the substances named are placed in order, each conducting better than those lower down on the list. A simple way of observing experimentally whether a body is a conductor or not is to take a charged gold leaf electroscope, and, holding the substance to be examined in the hand, touch the knob of the electroscope with it. If the substance is a conductor the electricity will flow away through it and through the body to the earth, and the electroscope will be discharged. Through good conductors the rapidity of the flow is so great that the discharge is practically instantaneous. Further information on this question is given in Lesson 33. 31. Distribution of charge on bodies. If electrification is produced at one part of a non-conducting body, it remains at that point and does not flow over the surface. Or at most flows over it excessively slowly, thus if a glass tube is rubbed at one end, only that one end is electrified. Hot glass is, however, a conductor. If a warm cake of resin be rubbed at one part with a piece of cloth, only the portion rubbed will attract light bodies. As may be proved by dusting upon it through a piece of muslin fine powders such as red lead, lycopodium, or verdigris, which adhere where the surface is electrified. The case is, however, wholly different when a charge of electricity is imparted to any part of a conducting body placed on an insulating support. For it instantly distributes itself all over the surface, though in general not uniformly over all points of the surface. 32. The charge resides on the surface. A charge of electricity resides only on the surface of conducting bodies. This is proved by the fact that it is found to be immaterial to the distribution what the interior of a conductor is made of. It may be solid metal or hollow, or even consist of wood covered with tinfoil or gilt, but, if the shape be the same, the charge will distribute itself precisely in the same manner over the surface. There are also several ways of proving by direct experiment this very important fact. Let a hollow metal ball, having an aperture at the top, be taken, as in Figure 26, and set upon an insulating stem, and charged by sending into it a few sparks from an electrophorus. The absence of any charge in the interior may be shown as follows. In order to observe the nature of the electrification of a charged body, it is convenient to have some means of removing a small quantity of the charge as a sample for examination. To obtain such a sample, a little instrument known as a proof plane is employed. It consists of a little disc of sheet copper or of gilt paper fixed at the end of a small glass rod. If this disc is laid on the surface of an electrified body at any point, part of the charge flows into it, and it may be then removed. And the sample thus obtained may be examined with a gold leaf electroscope in the ordinary way. For some purposes a metallic bead, fastened to the end of a glass rod, is more convenient than a flat disc, if such a proof plane be applied to the outside of our electrified hollow ball, and then touched on the knob of an electroscope, the gold leaves will diverge, showing the presence of a charge. But if the proof plane be carefully inserted through the opening, and touched against the inside of the globe and then withdrawn, it will be found that the inside is destitute of electrification. An electrified pewter mug will show a similar result, and so will even a cylinder of gauze wire. 33. Biot's experiment. Biot proved the same fact in another way. A copper ball was electrified and insulated. Two hollow hemispheres of copper, of a larger size, and furnished with glass handles, were then placed together outside it, figure 27. So long as they did not come into contact, the charge remained on the inner sphere, but if the outer shell touched the inner sphere for but an instant, the whole of the charge passed to the exterior. And when the hemispheres were separated and removed, the inner globe was found to be completely discharged. 34. Further explanation. Doubtless the explanation of this behavior of electricity is to be found in the property previously noticed as possessed by either kind of electrification, namely, that of repelling itself. Hence it retreats as far as can be from the center and remains upon the surface. An important proposition concerning the absence of electric force within a closed conductor is proved in lesson 21. Meanwhile, it must be noted that the proofs, so far, are directed to demonstrate the absence of a free charge of electricity in the interior of hollow conductors. Amongst other experiments, Turquem showed that a pair of gold leaves hung inside a wire cage could not be made to diverge when the cage was electrified. Faraday constructed a conical bag of linen gauze, supported as in figure 28, upon an insulating stand, and to which silk strings were attached, by which it could be turned inside out. It was charged, and the charge was shown by the proof plane and electroscope to be on the outside of the bag. On turning it inside out, the electricity was once more found outside. Faraday's most striking experiment was made with a hollow cube, measuring 12 feet each way, built of wood, covered with tinfoil, insulated, and charged with a powerful machine, so that large sparks and brushes were darting off from every part of its outer surface. Into this cube Faraday took his most delicate electroscopes, but once within he failed to detect the least effect upon them. 35. Applications. Advantage is taken of this in the construction of delicate electrometers and other instruments, which can be effectively screened from the influence of electrified bodies by enclosing them in a cover of thin metal, closed all round, except where apertures must be made for purposes of observation. Metal gauze answers excellently, and is nearly transparent. It was proposed by the late Professor Clerk Maxwell to protect buildings from lightning by covering them on the exterior with a network of wires. 36. Apparent exceptions. There are two apparent exceptions to the law that electrification resides only on the outside of conductors. 1. If there are electrified insulated bodies actually placed inside the hollow conductor. The presence of these electrified bodies acts inductively and attracts the opposite kind of charge to the inner side of the hollow conductor. 2. When electricity flows in a current, it flows through the substance of the conductor. The law is limited therefore to electricity at rest, that is, to statical charges. 37. Faraday's ice pail experiment. One experiment of Faraday deserves notice, as showing the part played by induction in these phenomena. He gradually lowered a charged metallic ball into a hollow conductor connected by a wire to a gold leaf electroscope, figure 29, and watched the effect. A pewter ice pail being convenient for his purpose, this experiment is continually referred to by this name, though any other hollow conductor, a tin canister or a silver mug, placed on a glass support, would of course answer equally well. The following effects are observed. Suppose the ball to have a plus charge. As it is lowered into the hollow conductor, the gold leaves begin to diverge, for the presence of the charge acts inductively, and attracts a minus charge into the interior and repels a plus charge to the exterior. The gold leaves diverge more and more until the ball is right within the hollow conductor, after which no greater divergence is obtained. On letting the ball touch the inside, the gold leaves still remain diverging as before, and if now the ball is pulled out, it is found to have lost all its electrification. The fact that the gold leaves diverge no wider after the ball touched than they did just before proves that when the charged ball is right inside the hollow conductor, the induced charges are each of them precisely equal in amount to its own charge, and the interior negative charge exactly neutralizes the charge on the ball at the moment when they touch, leaving the equal exterior charge unchanged. An electric cage, such as thin ice pail, when connected with an electroscope or electrometer, affords an excellent means of examining the charge on a body small enough to be hung inside it. For without using up any of the charge of the body, which we are obliged to do when applying the method of the proof plane, we can examine the induced charge repelled to the outside of the cage, which is equal in amount and of the same sign. If two equal charges of opposite kinds are placed at the same time within the cage, no effects are produced on the outside. 38. Distribution of charge. A charge of electricity is not usually distributed uniformly over the surfaces of bodies. Experiment shows that there is more electricity on the edges and corners of bodies than upon their flatter parts. This distribution can be deduced from the theory laid down in lesson 21, but meantime we will give some of the chief cases as they can be shown to exist. The term electric density is used to signify the amount of electricity at any point of a surface. The electric density at a point is the number of units of electricity per unit of area, that is per square inch, or per square centimeter. The distribution being supposed uniform over this small surface. Image A, sphere. The distribution of a charge over an insulated sphere of conducting material is uniform, provided the sphere is also isolated, that is to say, is remote from the presence of all other conductors and all other electrified bodies. The density is uniform all over it. This is symbolized by the dotted line round the sphere in figure 30a, which is at an equal distance from the sphere all round, suggesting an equal thickness of charge at every point of the surface. It must be remembered that the charge is not really of any perceptible thickness at all. It resides on or at the surface, but cannot be said to form a stratum upon it. Image B, cylinder with rounded ends. Upon an elongated conductor, such as is frequently employed in electrical apparatus, the density is greatest at the ends where the curvature of the surface is the greatest. Image C, two spheres in contact. If two spheres in contact with each other are insulated and charged, it is found that the density is greatest at the parts farthest from the point of contact, and least in the crevice between them. If the spheres are of unequal sizes, the density is greater on the smaller sphere, which has the surface more curved. On an egg-shaped or pear-shaped conductor, the density is greatest at the small end. On a cone, the density is greatest at the apex, and if the cone terminate in a sharp point, the density there is very much greater than at any other point. At a point, indeed, the density of the collected electricity may be so great as to electrify the neighboring particles of air, which then are repelled, see Article 47. Thus producing a continual loss of charge. For this reason, points and sharp edges are always avoided on electrical apparatus, except where it is specially desired to set up a discharge. Image D, flat disk. The density of a charge upon a flat disk is greater, as we should expect, at the edges than on the flat surfaces. But over the flat surfaces the distribution is fairly uniform. These various facts are ascertained by applying a small proof plane successively at various points of the electrified bodies and examining the amount taken up by the proof plane by means of an electroscope or electrometer. Coulomb, who investigated mathematically as well as experimentally many of the important cases of distribution, employed the torsion balance to verify his calculations. He investigated thus the case of the ellipsoid of revolution, and found the densities of the charges at the extremities of the axis to be proportional to the lengths of those axes. He also showed that the density of the charge at any other point of the surface of the ellipsoid was proportional to the length of the perpendicular drawn from the center to the tangent at that point. Rees also investigated several interesting cases of distribution. He found the density at the middle of the edges of a cube to be nearly 2.5 times as great as the density at the middle of a face, while the density at a corner of the cube was more than 4 times as great. 39. Redistribution of charge. If any portion of the charge of an insulated conductor be removed, the remainder of the charge will immediately redistribute itself over the surface in the same manner as the original charge, provided it be also isolated, i.e., that no other conductors or charged bodies be near to perturb the distribution by complicated effects of influence. If a conductor be charged with any quantity of electricity, and another conductor of the same size and shape, but uncharged, be brought into contact with it for an instant and then separated, it will be found that the charge has divided itself equally between them. In the same way, a charge may be divided equally into 3 or more parts by being distributed simultaneously over 3 or more equal and similar conductors brought into contact and symmetrically placed. If 2 equal metal balls, suspended by silk strings, charged with unequal quantities of electricity, are brought for an instant into contact and then separated, it will be found that the charge has redistributed itself fairly, half the sum of the 2 charges being now the charge of each. This may even be extended to the case of charges of opposite signs. Thus, suppose 2 similar conductors to be electrified, one with a positive charge of 5 units and the other with 3 units of negative charge. When these are made to touch and separated, each will have a positive charge of 1 unit, for the algebraic sum of +5 and -3 is +2, which, shared between the 2 equal conductors, leaves +1 for each. 40. Capacity of conductors. If the conductors be unequal in size, or unlike in form, the shares taken by each in this redistribution will not be equal, but will be proportional to the electric capacities of the conductors. The definition of capacity in its relation to electric quantities is given in Lesson 30, Article 271. We may, however, make the remark that 2 insulated conductors of the same form, but of different sizes, differ in their electrical capacity. For the larger one must have a larger amount of electricity imparted to it in order to electrify its surface to the same degree. The term potential is employed in this connection, in the following way. A given quantity of electricity will electrify an isolated body up to a certain potential, or power of doing electric work, depending on its capacity. A large quantity of electricity imparted to a conductor of small capacity will electrify it up to a very high potential. Just as a large quantity of water poured into a vessel of narrow capacity will raise the surface of the water to a high level in the vessel. The exact definition of potential, in terms of energy spent against the electrical forces, is given in the lesson on Electrostatics, Article 263, it will be found convenient to refer to a positively electrified body as one electrified to a positive or high potential, while a negatively electrified body may be looked upon as one electrified to a low or negative potential. And just as we take the level of the sea as a zero level, and measure the heights of mountains above it and the depths of mines below it, using the sea level as a convenient point of reference for differences of level, so we take the potential of the Earth's surface, for the surface of the Earth is always electrified to a certain degree, as zero potential, and use it as a convenient point of reference from which to measure differences of electric potential.